Good morning, this is Brandon with Trained by Techs. I'd like to have a discussion today talking about a scope functionality that's very common amongst almost all lab scopes nowadays, and it's called the trigger function. Now, like a lot of you, I tend to capitalize on the trigger function quite frequently because it allows me some capabilities that a free-running lab scope capture simply can't provide for me very easily. So I'd like to talk about some of the benefits that the trigger functionality of a lab scope can provide, as well as some of the downfalls if you're not aware how it functions. So this whole movie is pretty much about understanding the limitations of the tools or the test you're using, no matter what test it is or what core you're working on. Keeping that in mind helps you perform captures accurately and avoids making costly mistakes. Now, a lab scope is nothing more than basically a glorified DVOM, or digital volt ohm meter. It allows us the ability to plot what we measure as a potential difference across our two test leads over a period of time. Now, pardon the rough sketch I did here. I'm not an artist by any means, but what I'm trying to demonstrate here is a lab scope drawn on a piece of paper, ranging from 0 upwards of 5 amps over a time frame or sweep of 5 milliseconds. Now, the benefit of using a trigger functionality is the ability to command the lab scope to draw what it is we desire under certain criteria. For instance, if I were to set up my trigger in a position of a 50% of the entire sweep, I'm telling my scope not to begin drawing the waveform here or over here at the end, but right in the middle, about the 50% mark. A second aspect of a trigger setup would be a channel. In some cases, some scopes only have 2 channels, others have 4, some have 8, and some even have 12. But in this case, I was, as an example, chose channel 3. So I'm telling my scope so far, we're going to be looking at channel 3 and only begin drawing in the center of the screen. The third aspect is level. In this case, since we're testing in a domain for amperage, we're going to choose an amperage level we wish to capture data from. In this case, I chose 600 milliamps. And the fourth aspect, of course, is slope. In this case, a positive slope, or the rising edge of the waveform, rather than a falling edge. So if you combine all of these pieces of criteria, I'm telling my scope, I'm commanding my scope to draw under. I'm basically telling the scope, monitor channel 3, only draw the waveform beginning in the middle, or the 50% mark of the screen, when the rising edge achieves 600 milliamps. Once that happens, begin drawing the waveform right there and complete the rest of the sweep. And do not redraw the waveform until this exact trigger criteria is met again. So what I'm getting at is, following this criteria, I've commanded the scope, again, trigger off channel 3 at the 50% mark, and once the waveform achieved 600 milliamps on the positive or rising slope, begin drawing the waveform, everything before and after that, and repeat that same drawing if that same channel 3 achieves the same trigger criteria above. And what that does for us is allow us to view the waveform in a more stabilized fashion. Rather than having the data or the information come across the scope screen and appear almost random or erratic, it will repeat in the same spot and allows for a good looking view, an analytical view of what's happening. This becomes particularly beneficial in cases where, for instance, a stall occurs. Now, understanding that when a stall occurs and an engine is no longer running, obviously a spark is no longer being discharged. So if I were to monitor the current going through an ignition coil and I had adequate time on the screen, if I set my trigger criteria for that coil current and I placed it not here in the 50% mark, but I placed it over here in maybe the 90% mark, 90% of the sweep. If I had adequate time on the screen, when the stall occurs, of course we know spark is no longer occurring. So if I set my trigger for the falling edge of an ignition coil ramp, since the ramp would stop being produced, my waveform would be virtually paused on the scope screen. Even if I happen to step away from the vehicle and was not able to pause the scope's ability to capture, it would all be there. And because I placed that trigger criteria at the 90% mark of the sweep, everything leading up to the stall would be visible. So if I was capturing data pertaining to the command to the coil, as well as voltage supply, and the ability for the igniter or ignition control module or PCM or whichever ECU is responsible for driving that circuit, I could virtually diagnose the entire ignition system from one capture. Now, I mentioned earlier, triggers can serve us very well if we use them properly. However, if we're unaware of what they're actually doing and we don't use them properly, it could actually mask some problems for us and avoid us from properly diagnosing a vehicle accurately the first time, if at all. So if you bear with me 1 second, I want to show you something I want to try here, and to demonstrate what I mean by how triggers can hurt us or help us. I've got a demo board here that simulates an engine operating system by way of an ECU right here. We've got battery supply. In this case, I've got a supplemental input coming out of a wall outlet to power up this device here. So what I do is I'm going to be utilizing 3 channels of my scope being right here. We'll cover all that in some detail coming up. I'm going to take the ground reference of my scope and connect it to the ground reference of our virtual vehicle here. I'm going to take the red channel of my Labscope and we're going to put it here on my crankshaft position sensor signal. I'm going to be taking the yellow channel of my scope and placing it on the camshaft position sensor signal. And I'm going to be taking the green channel of my Labscope and monitoring the ground side or the control side of my ground side driven fuel injector circuit. So with my scope leads sampling from the points I just discussed a moment ago, we're going to quote-unquote start the engine, and I want you to listen to the rhythmic tick of the fuel injector as it cycles. We can hear it's got a steady cadence here. You can also see, might be hard to see in this light, a green LED that flashes every time the fuel injector circuit's broken. More importantly, if we come over to the Labscope, we can see that the fuel injector is being driven and it appears to oscillate across the scope screen at random. This is because we are in a strip chart or roll mode, sampling data at will. However, if I switch over to a triggered scope mode, I've set up my trigger criteria as follows. Channel 3 at the 10% mark at a level of 6 volts at the falling edge. So if you look closely, this might appear frozen, but the scope is actually sampling and redrawing at the same spot at the same time. Now here's where things tend to get interesting. As you can see here once again, you can listen in the background the cadence of that fuel injector pulse as it occurs rhythmically throughout the engine cycle. And my Labscope is set up to capture in a trigger mode fashion off the green channel number 3 on the falling edge at the 10% mark at 6 volts. It's repeating rhythmically. The downside to a trigger is that it can mask some faults. So if you look over here on my ECU board, I have the ability to introduce different faults to this fuel injector circuit. I'm going to introduce fault number 2 And what that's going to do is simulate a loss of camshaft position sensor input to the ECU intermittently. What that means is intermittently we're going to use lose an injector pulse event. I want you to listen. You'll notice the fuel injector pulses twice and it skips one and then repeats the process. But if we pan over here to my Labscope screen, although I am still triggering, still capturing on a triggered event, I will momentarily get rid of the fault. You'll have to listen while you watch the screen. You'll see virtually no change. So as can be seen on the demo board, when I introduced the fault and took the fault away, there is virtually no difference in appearance to what you saw displayed on the Labscope screen while the sample was being captured in a trigger mode. The reason being is, if you recall, a trigger is nothing more than a command to the scope screen to capture and draw. As long as that trigger criteria is achieved, the Labscope will draw the waveform as I desire it. The downside is it will keep that waveform on the screen permanently until that trigger level is achieved once again. So what I'm getting at is, even though we have a loss of signal, it's not represented on the scope screen accurately, and that's the downside to using a trigger. The benefit to using free run or strip mode, chart mode, is that it can capture data over a period of time. And I equate this to having the ability to capture a picture, a momentary capture of time while driving down the highway looking out the window. And as if you were looking into the woods and had a camera, if you took a picture, you'd get a single capture. And as you prepared that camera to capture once again, a lot of time would have gone by and you've missed a bunch of data. Whereas if you had a video camera running where you could capture this data as it continues to run or strip through a chart, you wouldn't miss anything. So the benefit to having a free run mode is that you don't lose data, whereas the trigger mode allows you to evaluate the signature or capture dynamically in one spot. Very easy. So now I'd just like to take a moment to display what happens when trigger level that you desired is not achieved by the scope. You might be wondering why your scope isn't recording, and you might think there's the problem when in fact it only has everything to do with the way you've set up your trigger criteria. So going back to the data we've selected for a trigger, obviously our scope is in trigger mode, as we can see here. We've got 40 milliseconds of sweep on the scope. Oops. We're going to set our scope trigger at the 50% mark. That's where we want to draw the waveform. Of course, we're going to be triggering off channel 3. You can see here we set our slope on the rising edge above 74 volts. What that means is I told the scope screen, begin drawing when the green channel, channel number 3, achieves 74 volts on the rising edge, and draw it right in the center of the screen at the 50% mark. So what we can clearly see here is on the lower scope we're free sampling, proving to you that we do have a signal going across the screen. But the top screen, is not sampling. It might appear that way. The truth is, it is sampling, but it won't draw on the screen because we've asked for 74 volts rising. And that's indicated here by this triangle, 74 volts. So I've set a trigger level that the waveform being acquired is not yet achieved, and it looks like there's no signal on the screen. But if I were to simply take my trigger level and take it down to a more reasonable level, in this case 50 volts, we can see here that the waveform achieves over 60 volts, which means at this point in time we've satisfied our trigger criteria. So keep in mind, if you don't set trigger up properly, you can miss a lot of data. Now again, having the scope free running, With a normally operating injector, as you can hear by the sound, the cadence of the injector firing, it's relatively steady over an entire engine cycle. And when I reintroduce the fault, you'll hear the change, but you won't see the change here. I want to show you a different aspect of the scope I'm using. Not that it matters, but I'm using an ATS eScope Elite 4-channel Labscope. And what I want to show here is a functionality called dual time bases. What's neat is that I can maintain that analytical view I desire on the upper Labscope screen. However, on the bottom Labscope screen, I can run it in a free run strip chart roll mode, where I can see all the information. So again, going back to the analogy, this would be like a camera taking a still photograph once periodically, and this would be almost like a video camera recording the data live as it happens. Watch the difference when I reintroduce the fault again. As you can see on the upper Labscope screen, there's virtually no change because of that trigger functionality. However, you can clearly see it visible on the lower screen. So what I'm going to do, if this simulates an intermittent misfire, I'm going to hold this data and pause it on the scope screen. And I'm going to turn this off just to get rid of that background noise. But what we can see here, scrolling through this data, we can see that periodically it's dropping out. The green injector pulse width is missing here. So what I'll do now is I got to ask myself, why would an injector pulse drop out? Could it be due to a faulty computer driver? Could it be due to a loose connection or a broken wire? Could it be a bad output due to a bad input? And the answers to those questions are all yes. The difference is finding out why. So in this case, I'm just going to go over here to my measure and deep record screen. And I'm going to plot B. And what I can see here is, again, panning through here, we see 2 injector pulse widths and then a missing one. And then we see 1, 2, 3 events and then a missing one. And then another 3 events and a missing one. So the question becomes, why? Well, for now, I'm going to turn off my injector pulse, where I'm only looking at my camshaft and my crankshaft position signals overlaid upon one another. Both 0 to 5 volt signals. I'm going to add oops. 5 volts offset here to my camshaft position sensor signal. And if I pan, I can clearly see every time I have an injector pulse, it's due to first an input from a crankshaft position sensor, a camshaft pulse. Cam pulse, injector pulse. Cam pulse, injector pulse. I have no injector pulse, but I also have no camshaft pulse. So as can be seen, where the missing green injector pulse width occurs, there's a correlating missing camshaft position sensor pulse signal. So this area here, and this area here, and right here, you can see that the signal's missing. So at this point in time, what we then have to do is go back to the vehicle and evaluate the camshaft position sensor signal. We have to see, first of all, is the cam signal actually emitting, the cam sensor actually emitting the cam signal from the cam sensor. If it is, Is it simply not making it to the PCM? That's what we need to determine. So hopefully by now it's clear for you to see that a trigger can be extremely beneficial to Labscope capture capability, as well as your ability to properly analyze the health of the circuit when it is functioning. However, trigger can also hinder your ability to detect a malfunction if you're triggering off a circuit that happens to intermittently fail. So having the ability to monitor the circuit in a strip chart or a roll mode, where you can evaluate data in a video type format, a long rolling chart of everything that's being acquired, and also having the ability to analyze data in a triggered format to get more of that analytical view so you can monitor the health of the circuits when it's functioning, provides the best overall evaluation of the circuit in its entirety. And it's clear to see from this failure that by determining the injector intermittently fails to drive the green trace that we saw dropping out, we then have to ask why. And why means determining, does the PCM have everything it needs to drive the injector? If the answer is yes, and the PCM is not driving the injector, clearly a driver's at fault. We then have to ask, why did that happen? Was it due to a failure, due to an overcurrent draw, like a shorted injector? Or is it simply just a bad driver in the PCM? Or a logic error? These things happen. And to determine what happened, what the root cause failure was, means having to answer the questions that we ask of our Labscope. So I hope you gained some insight into how triggers can both help you and hinder your performance. And if you have any questions about any of the tools we used today, how we went about implementing the test to determine what might be wrong with the vehicle, or any questions regarding Labscopes at all, please don't hesitate to ask. You can reach us at trainedbytechs.com and also find us on Facebook. Thanks. Again, my name is Brandon Steckler with Trained by Techs, and we appreciate you guys watching. Take care. Have a great day.